So we said that we can make any Boolean expression using just ands, ors, and nots. But it turns out that NAND is a very special type of gate because NANDs can do it all. NANDs can do everything just with themselves, just NAND gates. So really, if you want to stock just one part, you should stock a bunch of NAND gates. Actually, if you look at some advanced designs that might go into your computer or processors or microprocessors, they might mostly be based off of NANDs. There's another reason for that as well. It's actually, when you look at how a NAND gate is made, something that we'll do later, you'll see that it uses the fewest amount of transistors, so it uses the least space. But anyway, let's see if we can make some arguments for why NAND is a complete logic set all on its own. So what we need to do is we need to prove that you can do the not function, right? So, oops, not mot. Not. And we need to prove that we can do the and we also need to prove that we can do the or function. So let's just get started with the easy step here, which is the not. And so there's actually a couple approaches that we'll use in proving this, and it's kind of a little bit of an intuitive argument here. So the first thing for the not, we notice that if you were to if we look at the truth table, we can look at spots where we have 0 as the input and 1 as the output, and 1 as the input and 0 as the output. And it's kind of something interesting that we notice here. When they're the same, or these two rows here, right? When we have two zeros, the output's a 1. When we have two 1s, the output's a 0. So, what if we just took a NAND gate, right? So it looks like an AND with a not on it. We have our two inputs, and we tie them together, right? So we've got A here. And let's just see what happens if we say A is a 0. That means, I guess I should give this a different name. Let's call it M with a fancy little line on it now. So M is our input variable. So that means here in our truth table, A is a 0, B is a 0. Our output is 1. If M is a 1, that means A and B are both 1, and the output's a 0. So therefore, we can conclude that this output is M naught. So it's, I guess, admittedly, it's not super straightforward, but I would still say it's kind of an intuitive argument based off of the truth table. Now, for the AND gate, if you want to make an AND gate, we can kind of think about what a NAND is. A NAND gate is just it's just an AND with a not on it. And we know that if we not something twice, so we invert it and then we invert it again, we end up with the function we originally had. Meaning, if I have an AND gate, or a NAND gate, and I invert it, I should end up with just an AND gate. But we don't have an inverter, right? We only can use NANDs. But we do have a NOT gate now, right? We do have an inverter, and that's right here. Oh man, I'm so sorry. So what we can do is we can do a NAND gate, and then we take that output and we split it to go to both of the inputs on another NAND gate. And so here we can have we'll say x, y. And so let's just test this out. If we have x is a 1 and y is a 1, and we feed that through a NAND gate, x is a 1, y is a 1, so that means here this is a 0. And then that 0 passes through an inverter, and the output is a 1. Let's test that for another value. Let's test 0 and 1. So we've got 0 here and 1 here, so you got a 0 and a 1. That means the output is going to be a 1 here. And that 1 gets inverted to a 0, which is the function that we want for an AND. So here we've got x and y. So this one we just kind of looked at the truth table for the NOT. The AND gate, we kind of looked at the truth table and just kind of thought about the way the gates work and kind of the definition of the gates. The OR gate, we're going to look at mathematically. So let's just write down the function for OR, right? We've got x or y. And as I said before, one of my favorite things to do when analyzing a Boolean expression is to find the De Morgan equivalent. When you find the De Morgan equivalent, it gives you a whole another realm to work with, but it's still equivalent. So if I want to find the De Morgan equivalent of this statement here, I'm going to invert the inputs, and so we got x and x naught and y naught now, and our ORs change to ANDs. And then the last step, remember the De Morgan complement and the De Morgan equivalent are different things. Right now we have the De Morgan complement. To get the De Morgan equivalent, we put it in parentheses and invert the output of this function. So we can say that these are equal, and I like to write DE over it, right? This is the De Morgan equivalent. Now, whenever we have, just kind of as a side here, we have something ANDed with something knotted, this is the AND function knotted, or this is the NAND function, right? This is what the NAND function looks like. So technically we have x naught NANDed with y naught. So we have a NAND function already here now. We've got a NAND function, and then we just need to invert x and y. And we can do that because we've proven that we can make a NOT gate with a NAND. So that means what we need to do is we need to invert x and y. So let's do that first. So x is going into both inputs here, x, and we need to invert y. So y goes into both inputs there. And then we just need to feed it into our NAND gate again, another NAND gate. And what do we end with? X or y. So these are kind of a bunch of different forms of argument that we can make to prove these. But if we can make a NOT, an AND, and an OR from just NANDs, and we can do any sum of products expression with NOTs, ANDs, and ORs, that means that NANDs are also a complete logic set.